Ieslēgtas nav tik svarīgi. Kamēr var atslēgt? Būtu atslēgts, es parādīšos uz brīdi viņiem. Nu tā, es varu ieslēgt viņu. Good morning, everybody. I've had a little bit of technical problem for some reason, so I have been a little bit late, and you got thrown out because that previous meeting actually stopped. So that's something that happened. I will probably switch off the camera now so that you can focus on the presentation and on the material. I myself am not so important, although on the other hand, why not? Why not? I can leave the camera on. So I will, in fact, pull this a little bit away so that we can see exactly what is going on. So once again, so if you have some friends who are shouting that they couldn't join anything, let them know that everything is okay now, so we can simply go on. So I will probably, stretch this a little. It doesn't stretch. Okay, we have to do it with this. Let's see, can I stretch this out a little bit? I don't want it to take up the whole screen, but there we go. Yes. That's it. That's it. So let's put chat somewhere up there. All right. So there we go. Once more, for those who are joining just now, I'm very sorry about the delay. I had a sudden, very unexpected problem with my Orthos password, so now that's fixed now, and we are now ready to start the lecture. So last time we introduced differentiation as such. We had some first few rules. Okay, it's not working, so I have to do it manually, I guess. Okay, I'm doing it manually now. So what we did, so first of all, let's just remember that we had this limit, delta f divided by delta x, where delta x tends to 0, and our understanding of that was we had, we had a function and we said, all right, we choose a value x, and I denoted by x0 last time. We add delta x, so delta x was this segment, and we were considering the difference between the two function values. This is the delta f, and this is delta x. And we said that actually this ratio, or the slope of the secant line looked like this. The secant line becomes more and more of a tangent line if delta x becomes very small. In other words, if this triangle becomes very small, then the boundary situation, the extreme situation of the secant, is actually that of a tangent. And therefore, the slope of this tangent line is what we call the derivative of the function f. At the same time, we saw that it is, on one hand, the slope of the graph, the steepness of the graph. At the same time, it is also the instantaneous rate of change of the function or of any process that this function describes with respect to time or with respect to anything else. And of course, the most common interpretation is velocity in the motion. We will discuss interpretation of derivative as velocity, as the process of motion. And so we had just a few rules last time. So we saw that the derivative of a power, x to the power a, can be found by putting the exponent as coefficient in front. That would be this. And the exponent itself for x is decreased by 1. And not all x, I am sorry, this had to be for all a values. So any exponent whether it is an integer, a positive integer, negative number, positive number, rational number, irrational number, for absolutely any value of the exponent a, which means this works for all the roots, this works for all the quotients, 1 divided by x to some power, because that means the exponent will be negative, and so on and so on. So this is pretty universal. Then we saw that we can multiply the function by a constant. That would simply mean that we multiply the derivative by the constant, and that's it. If we want to differentiate a function that is multiplied by some constant, that means that we can multiply the function's derivative by that constant and get the correct result. And finally, if we have the sum or difference of two functions, then when differentiating a sum or difference, like in polynomials, for example, we can differentiate term by term separately, term by term. And this is what we already quite successfully did last time. So this is the beginning. What I said also last time was if we have a product or a quotient, the direct differentiation doesn't work. First of all, and using limits is of course something you would not like to do, because limits can be rather complicated at times. However, if you have a product, you can try to open the parentheses and differentiate term by term, one by one. Unfortunately, it's not always possible. Sometimes you have products where you just cannot open any parentheses, especially when the functions become more complicated. And so let's see the chain rule. So today we have three more rules: the chain rule, the product rule, and the quotient rule. The chain rule is used if we have a composite function. Now you have to think back a little bit. You have to think back to the functions and limits to fourth unit beginning, when we discussed functions as such. Remember, a composite function was a function of a function. That is, we have a function f of some variable u, but the variable u itself is found using some other rules from another variable. So basically, we have the function f of g of the independent variable x. So how do we differentiate this case? So actually the situation is quite interesting. So we say, all right, we want to differentiate. I will choose white, and I guess I need to take the highlighter, because does it work? No, it does not. And if with white, it does not.
Yes. Before that, I'm not able to send my name as a.
I saw it. No, I saw it in the chat.
Yeah, it's only coming exactly to you. Remember, you said you want us to.
Oh, you can only you can only send message to me. Okay, yes, that's because I am in a place where they don't see things automatically. That's fine. I will save the meeting chat and get it for myself. It's all right. It's all right. So in principle, I guess I can click something to enable everybody to message everybody, but at the moment, if someone has a question, type it there. I see it on the screen, and I'll try to answer. Okay, so pen white. So we want to differentiate, and this is the moment where I actually do want to write use the Leibniz notation, dy by dx, which is something that I generally do not like much. There are reasons for that. But in this case, we want to take this function, this whole expression, y, as a function of x. However, there's an in-between. There is an in-between this function g of x, and then f is taken of that. As a result, of course, y is a function of x, so we want to differentiate it by x, the independent variable x. However, how do we do this? So now, in fact, we do a little trick to prove or to find a new rule. So I will do it. I will divide by du and multiply by du. It is at this moment, this is very formal. This is very formal. So I introduce these two additional identical factors. It's very formal because in principle, if I write dy by dx, do we really understand it as a quotient of two things? What does it actually mean? And so on and so on. So this is a problem for the future. This is a problem for the future. At the moment, you have to trust me enough to say that even though dy divided by dx is not the same as delta y divided by delta x, we can actually afford to do this. In principle, we could translate this to limits and demonstrate that this is allowed, that this is possible, that this does work. But now what we see is derivative of the function y, which is f actually, the function f, differentiated by u, by this variable that can be obtained from x, times the derivative of that g function of u by the independent variable x. So how does that show up? How does that show up in the traditional derivative form? It looks like y, okay, no, that it looks like y derivative, and I'm using the regular notation again, or we could say the function f of g of x derivative is, we first of all differentiate the function, outer function, the f function, the outer function, the function that depends on this expression u. And we differentiate this by u, and then multiply by the derivative of the u differentiated by x. So we have to understand very well. There's one thing that is the most important thing. The most important thing is to understand what exactly is the inner function, the interior function, and what exactly is the exterior function, what operation is the outer function, so that we get the correct derivatives. Just a moment. Okay. Okay. Yes, if somebody is accustomed to use dy by dx, that notation, yes, because in principle, I can quite easily recognize those people who do it by themselves and those people who cheat using applications, direct applications, because a direct application will give you so detailed solution that it takes the whole page, whereas if you do it by yourself, it takes one line in that page. So I warn you against using all those magical applications which will solve your problems by magic. I'm perfectly aware that they exist, and I perfectly well can recognize when a student is using such an application. I'm warning you against that. That is one of my, let's say, pedagogical main reasons why I don't like this notation. But basically, if somebody is used to doing this, then I can recognize who is familiar and feels easy and good with this and comfortable with this, and who is just copying.
Miss, the thing is, like, when I did this in school, we barely used the other notation. We only used dy dx. And
okay, that's fine. That's fine. That's fine. Use it. Go on. Yes, yes, yes.
It's easiest to use, like when we use chain rule or like product
for chain rule, yes. For chain rule, yes. Yeah, however, if you are just doing it very, very quickly, a quick derivative, the quick differentiation, where you see clearly what you are doing, you can use this dash notation, the prime notation, because it's very quick. Because it's very quick. So sometimes it's very useful. You just write, okay, the function, dash, and shoot it off. You don't have to write dy dx. Okay, so the chain rule now in the printed form, okay, this didn't work. In the printed form, okay, sorry, continuous functions. So the thing is that functions have to be continuous. Let me remind you, a function can only be differentiated if it is continuous. So otherwise it's impossible. Then when we want to differentiate the function f of u of x, well, I didn't write g here, f of u of x, then first of all, you differentiate the function by the variable u, which is generally an expression, and that's why it might be confusing at the beginning. And then the inner expression is differentiated again. So that would be this thing. Now let's have a look at some examples. Let's have a look at some examples. In this case, let's see which is the inner function and which is the outer function. In other words, which is g and which is f, which is u and which is y. So we see that the outer function here, it's quite obvious, it's visible, it's obvious. So we can say that actually y, the f, okay, the f, let's do it, okay. Eraser. Let's see, we say that f of u is evidently square root of u. And then when we know what the square root of u is, we can, in fact, differentiate this. Now, u, okay, what's this pen? And this was there. Then we understand that u, on the other hand, well, then u of x is actually, okay, where was my expression? 4x squared plus 6x minus 1. With a little bit of experience. So first of all, those of you who have been doing this a lot at school have no problem whatsoever. You don't even have to write this out. I am doing this slowly, explaining things for those who are doing differentiation for the first time, who have never done it before at school, for example, for those people for whom this is new. So we understand this is simply sorting things out, like taking inventory. I understand my outer operation is taking the square root, and my inner operation, inner function is 4x squared plus 6x minus 1. And now I understand that df by du would be 1 divided by 2 square roots of u. Remember, that was a special case. One of the special cases, how to differentiate the square root. And the differential, the derivative of u by x is 8x plus 6. And now the answer, what?
I have a doubt.
What? What's that? Who is that? Who is that?
My name is Diz.
Why are you here?
These nuts.
Mm-hmm. And so what we see here is we see the two derivatives from the formula. We see this and we see this there. So all we have to do is multiply correctly. So y derivative is, as a matter of fact, from this function, f derivative, that is this expression, but we have to put the correct expression in u, because you see what's happening here. We do not have any u. We invented, it's like a temporary variable, like an invention and something in between that makes it easier for us to understand what is going on. So I cannot write u in the final answer. I have to write that expression for u. So that would be 1 divided by 2 square roots of not u, but 4x squared plus 6x minus 1, and multiplied by du by dx, that is by 8x plus 6. And of course, we see that we can simplify this a little bit. We could divide out 2. You could have 4x plus 3 divided by just the square root. So I need the bottom of the page for another example. I forgot that. Okay, on this board I write larger letters. So the final answer will be 4x plus 3 divided by square root 4x squared plus 6x minus 1 under the radical. That's the answer. That's the solution. That is the derivative. So in principle, we have to understand that when we differentiate the square root, it's only the outer thing, only the exterior function. We do not really touch the inner function. See the derivative. We simply differentiate the square root, but the inner function, u, remains as it was. We don't change that. But then we multiply by the next derivative of that inner function. Sometimes we have more than two links of the chain. It's called chain rule because we are linking these derivatives together. If the function is even more complicated, f of g of h, for example, then we would have three in between, three derivatives to multiply. So we are forming a chain, but the thing to remember is it's like an onion, like peeling an onion or like peeling a cabbage, one leaf at a time. One leaf at a time, starting from the outside, or like opening a box inside which we have another box, inside which we have another box, and so on. We cannot open the boxes inside before we have opened the outer box. That is, before we have differentiated the exterior function, the outer operation, that is the square root. Now we have differentiated the square root, open this outer box. Now we say, oh, inside the square root, now we have 4x squared plus 6x minus 1. Now we differentiate that and multiply. And if it is a composite function itself, then we go inside still and have a third factor. We will have those examples.
Miss, I have a question.
Yes.
So, like when I did it in school, right? We don't like for this question. We don't even use chain rule. We'll just know it by recognition. Like so, like.
But that is chain rule. That is chain rule. The thing is, I already said this is something that is to help those people who have not done this. An explanation how to approach, because when you just start differentiation, and this is just the second lecture for differentiation, and if somebody has not done this ever before, then at least an explanation of what is really going on is in order. We will very soon, in just a few examples, we will be able, hopefully, to do without this extra stuff. We will be we'll be able to do it by recognition.
For example, we will just have some just example like 4x plus 1, right? And it will just make this part.
Yes, we will. Yes, wait. This is
4x squared. Whatever we have inside, we'll just differentiate the inside part, and we'll and put that outside. So it will be like 4x now, right? 4x, and we'll just keep this part in.
No, that will be 8. But okay, yes. But with that's the whole problem. With practice, it happens like that.
Right.
But without practice, some people would feel rather lost. Some people would feel rather lost with this just immediately. So the important thing is to recognize what is the inner function, what is the outer function. Once you have learned to recognize that easily, then chain rule becomes actually easy indeed. I agree. So the second example, yes.
And miss, but if in the exam, right, you're asked to calculate, you're asked to differentiate this equation, do I need to do all this work, or I can
no, you do it. You do it as you feel comfortable. Do you do it as you feel comfortable?
I want to know if I lose mark if I don't use.
No, the problem with losing points is that I hate cheaters, and I have to fight against those. So if some obvious work is missing, something that you cannot write, and I know that person cannot do that in their mind. So that's what creates a problem. I know fairly well who can do things and who has to resort to other measures. Example 2. This is simple. You see, the outer function is taking something to the 10th power. How do we differentiate the 10th power? We had the rule. So in this case, I will try to write the answer right away, except that I will do an explanation. So first of all, the f function of u is u to the 10th power. So we will have to differentiate 10th power. And the u function is 5 minus 2x. That's fine. That is fine. So first of all, we need to differentiate the outer function, that is the 10th power. We know the 10th power derivative is 10 times base to the 9th power. Okay, so it's 10 times base to the 9th power. And then we need to multiply this by the derivative of the inner function. The inner function is 5 minus 2x. Its derivative is, of course, minus 2, the constant at x. So my final answer will be minus 20, 5 minus 2x to the 9th power. Yes, I'm sure that there are people who can write the answer immediately. No problem with that.
Yes, this is the kind of question I was talking about, Miss. Like,
Yeah.
you don't have to do all that because it's an easy question, right? So we could just write the answer one time.
The thing is that there will be some difficult questions where you will feel that you need to write something down so that you don't make a mistake.
Yes.
Yeah, that's natural. That's okay. That's understood. That is understood. Okay, so this actually illustrates a special case. This illustrates a special case when the function g is the inner function, is linear function, like this. Linear function kx plus b, that would be this function. It's linear. In that case, of course, we understand the derivative of the linear function is simply the coefficient k. We saw that last time. And so that means that when the interior function, when we see that we have f of kx plus b, a simpler case, a simpler special case, then the derivative would be k times the derivative of the outer function itself. So just like that. So in this case, in my example here, I am sorry about this mess with writing, because it was generally not expected to happen like this. In principle, with this example, I would say, okay, the interior function, the inner function is this, 5 minus 2x, its derivative is minus 2. And so I have to multiply derivative of 10th power times minus 2. And in this case, of course, the derivative of 10th power was 10 times 5 minus 2x to the 9th power. The base is the same. It doesn't change. But its derivative is minus 2, so I multiply it by the coefficient 10, and so I got this minus 20 in the end. All right, I have to move on. I have more examples. So in principle, as you see, it looks like this without any other situations. So we first of all, the thing is, you have to understand what order you do the operations. The differentiation goes backwards. We start by differentiating the outer operation, and then we move inwards and do one differentiation after another. And chain rule, because we multiply all these products. Because if we have, of course, if I have f of g of h of x, a more complicated function, then I take outer function f derivative by whatever variable, then times g derivative, then times h derivative. The thing is, we have to sort out those variables a lot. This is not the easiest way, and I know people generally make a lot of mistakes. Okay. Another example for the same. So 1 divided by some expression squared. So this looks perhaps a little bit confusing, but let's just rewrite this. Okay. Let's just rewrite this. as square root plus 2x to the power minus 2. Because it is in the denominator, we can easily imagine, so we have a negative exponent. And now we have again a power of some expression. So the derivative of the power, let's remember what it was. So if I want to differentiate this is basically why I'm writing with a prime, because that's much faster. So first of all, we have to differentiate the power minus 2 because it's the outer function. Power minus 2 derivative is minus 2 power subtract 1, right? What is inside? The same as it was there. We don't change the inside because we are only, at this point, I am only differentiating the outer function. And so inside we have square root of x plus 2x times, of course, now I need to multiply by, and many people would like to write it like this. Okay. Looks like I have to throw out some people. Whom should I throw out? Okay, again that thing. And I have to differentiate the inner function. So anybody who is responsible for inviting strangers in here, please stop that. I understand that there are some people who want to have just some fun at our expense, but you know, that's something like a 12-year-old could do. And so I have to still multiply by the derivative of the interior function. So at first, I will use this yellow. At first, I take and I differentiate. What is that? At first, I differentiate the power minus 2. That is, I do this, but I only change the power. You see, I only apply it to the power. I don't touch the inner function because the inner function is the next box inside. So after I have opened the outer box, the first box, by differentiation, now I see, okay, I have reached the next box, which is this expression. Now I will differentiate that one. And so we have minus 2 divided by, evidently, square root x plus 2x to the third power, because 3 is negative. Now we have exponent minus 3, which means we have a cube in the denominator, times the derivative of this, which is 1 divided by 2 square roots of x plus simply 2.
Class
Again? Okay, so at the moment, yes, we could simplify this somewhat. At the moment, we will not do it, but in principle, yes, we could pull things together a little bit on the same denominator, simplifying this algebraic expression. At the moment, we will not do that because it's time for us to move on. And so today, the next two rules, product rule and quotient rule, those are simple. Those people who know these rules know that they are not so difficult. However, they are not straightforward either. It's not like u derivative times v derivative. That would not be true. And that's the whole problem. So when we have a function that is actually a product of two functions, we have to be very careful when differentiating. The derivative would be, and now it is really easier to write with dashes, rather than d by dx. This means, so I will write it very shortly, u v without u of x, v of x. We will simply understand that u and v are functions. And so the derivative of the product u v derivative is u derivative times v plus u times v derivative. In other words, yes, we do differentiate both factors, each of them, but not at the same time. We differentiate the first factor and leave the second factor as it was, plus then we leave the first factor as it was and differentiate the second factor. And that's it. And that's it. So yes, it's not just derivative times derivative. So this is not difficult to do, but at least it's not just derivative times derivative. Now
Miss, but you said you use dy prime, but if I'm custom using dy dx, I could still use dy dx, right?
You can use it. It takes about double time to write, of course, but you may use it. Yes, of course.
Okay.
You can use it if you like it, although in, let's say, in everyday situations when all we want to do is do things very quickly, then it's not so very awful. All right, so y derivative would be, I'm writing slowly, x cubed minus 2x squared minus 3. This is the u function. This is the u function. So I differentiate that and multiply by the square root derivative x cubed, not the derivative, but the factor x cubed minus 2x squared minus 3 as it is. And I want to differentiate this nice square root. At this moment, I have not differentiated anything yet. So this is actually, again, at the beginning, when you just start derivatives, at the beginning, it's very good. What I did, I simply copied the product rule. This is the product rule. I just copied the product rule using my functions, not writing uv, but using my functions. Of course, it doesn't matter which of the two terms comes first. However, I would advise you to start differentiation by the u function, by the first function, because otherwise with quotient rule, you might be confused, because in quotient rule, the quotient rule is not symmetrical. The product rule, you see, is perfectly symmetrical. One function differentiated times the other one not, plus the other way around. So now I am going to do the differentiation. So the first factor, the u derivative, would be 3x squared minus 2 times x squared derivative is 2x, so that would be minus 4x. 3 derivative, you remember, constant derivative is 0. So that's the derivative of the u function of the first factor times the second factor, unchanged, plus, now the first factor is unchanged, times the derivative of the second factor. Remember, now this is actually a composite function, square root not of x, but square root of something. So we have to use the chain rule now. Derivative of square root is 1 divided by 2 such square roots, and times the derivative of the function in the square root, in the radicand function. The derivative of this is, of course, 5. So this is the answer. This is the solution for this particular example. Yes, we might want to pull things together on the same denominator. So we might write, I will probably have to erase this for the second example, for the next example. So we might have something like 2 square roots in the denominator, minus 6, which means I need to multiply by 2 the 2 square roots to pull the first thing on the denominator. But then you see we have 2, we have 3x squared minus 4x, and square root times itself, we lose the square root. So the numerator becomes rational. There's no more square root in the numerator. There's only one square root in the denominator, and then plus 5 times this. And then, of course, you can still open the brackets, combine the similar terms, and you would get a shorter expression in the numerator. So I am not finishing this at the moment. There's not enough time for that. But in principle, this looks already much nicer than the first result that we had. So this is the answer. This is the correct answer. Yes, you may leave it as it is. However, in the future, we will need to simplify the functions like that. So we will need to pull things together and to investigate what is going on there. So this is the answer, but it looks nice if you can simplify it. At the moment, that's not so important to do it. Now, next, for the quotient rule. For the quotient, evidently, u divided by v derivative, the quotient of two functions. The derivative is, well, a little bit more complicated than the product rule. We have u derivative times v without, minus u times v derivative, and divided by v square. It's not the derivative, it's just v square. So first of all, we see a fraction, an algebraic fraction. We write the denominator squared, and then we do basically the same thing that we did for the product rule in the numerator, except that there's a minus. And here it is important which function comes first, and which function comes second. That's why it is, let's say, advisable, it's very good to begin with the u derivative even in the product rule. Make it a habit, then you won't make a mistake. Because if you start differentiation by v in the product rule, it means that for the quotient rule, you might again do something whatever accidentally wrong, for example, being careless. So just making a good habit is starting the differentiation with the first function, with the u function always. If you do it even in the product rule where it is not strictly necessary, then you will form a habit, and that habit will help you to do the quotient rule always correctly. All right, I think I have an example. Yes, I have an example. So the next example will be a quotient. We will do it exactly in the same way as we did example number 4. So it will be, now I am erasing. Yes, I said I have to erase this. I have to erase this so that we can work on. And as I said, this part was not essential now. For now, it's not essential. However, in a test, I would be very happy if you simplified at least a little bit until it looks nicer, pulling some things together, pulling together the things that you can. And we did have a parenthesis here. Okay. Now for this, y derivative is, so this is the u function and this is the v function. So u function derivative times v function as it is minus u function as it is times v derivative divided by, of course, the square of v. As I said, there will be a couple of people who don't need to write it like this, who can write the derivative immediately. So who can write immediately this, like x squared plus 4 derivative is 2x, you just know it, it's simple, times 2x plus 1 untouched minus x squared plus 4 untouched times 2x plus 1 derivative is just 2 and divided by the square of denominator. Here, it would be actually very good to open the parentheses to simplify the expression. I'm not doing the algebra at the moment. However, it would be good if it's a rational expression like this. If it's not very complicated, then it is actually also very easy and quick to simplify this. We did that kind of thing in elementary mathematics at the beginning with the basic algebra. So here we would have 4x squared minus 2x squared is 2x squared plus 2x minus 8. Okay, we can in fact pull these things together, open the parentheses, simplify it, because it looks nicer, is more, well, it's easier to read and understand. And finally, the special case. If we simply have a function 1 divided by v, 1 divided by v. V function is something familiar, and we have 1 divided by v. Then its derivative would be something, again, fairly simple. So we would say 1 divided by v derivative is 1 derivative, which is 0, constant. So derivative of constant is 0 times the function v minus the constant 1 without derivative times v function with derivative, divided by v square, of course. So we see that the first term simply disappears. Always keep in mind, there are sometimes people who like to use quotient rule directly in cases like this. It could also be found as v to the power minus 1. But this is a bit messy, because now here you might think, oh, is it the inverse function? No, it's not. So you know that we don't like this minus 1 for inverse functions, and we have to be very careful. We have to be very careful with this kind of notation, so that you always have it clear in your mind what you mean when you write something. But here, in this case, we see it's minus v derivative divided by v square, because the first term is 0, and in the numerator it simply disappears. So that's a special case. Sometimes it is very useful. And so here we have it again written normally, in the normal way, in the normal form. We could, in fact, imagine, so if I have a function to differentiate 1 divided by 3x squared minus x plus 7, and I want to differentiate this. As you see, I don't particularly use this dy dx notation. However, if you are used to it and if you understand it, I will see if you don't. I will see if you don't understand it. So according to this special formula, I could simply say, okay, 1 derivative times the quadratic expression minus 1 times the derivative of the quadratic expression. But I could just use this special case formula, and I would say, okay, it's minus derivative of v is 6x minus 1 divided by v squared. And that's it. Of course, we can open the parentheses and write 1 minus 6x in the denominator. To simplify things, I can write 1 minus 6x divided by the same square that I have there. So that's what I meant by this special case for quotient rule, because it makes things much easier. If you look at that formula and you apply it, if you see 1 divided by some function, okay, we can do it. So today, as you see, we are not actually going into more complicated functions. We are not going into other functions. We are still stuck, in a way, with powers and radicals. That's not bad. Next time, that is on Wednesday, we will start differentiating many, many different functions. So actually, if you want, you can already check the lecture 5.03 the third lecture, which has a list of all derivatives for all elementary functions. Derivatives for all functions, a list. You can print it out for your use. You can use it at all times. And so we will basically only do exercises next time. These rules of differentiation plus the list of all functions with their derivatives. That's next time. No new stuff. Well, new stuff, yes. New functions. Trigonometric functions, exponential functions, logarithmic functions, all that. Yes, of course. So you will have to get used to other functions and their derivatives as well, but no new rules. No new rules for that. So, some more examples. In this case,
Look, I have one question, right? So like when we differentiate a certain number, we get ln of its. It's like ln x when you differentiate. I think I don't know. I'm not really sure. I can't remember. It's for integration.
where? In which was it in the previous slide? Which part?
No. It wasn't. It wasn't. No, I'm asking a new question, right? So
Okay, a new question.
yes. So like when I did differentiation and integration in school, right? We had this where when you differentiate, you will get a certain number which will be ln x. Because
ln x,
yes.
natural logarithm, you mean?
Oh, we will do natural logarithms. We will do next time natural logarithm. The thing with natural logarithms, derivative of natural logarithm function is 1 divided by x. Integral of 1 divided by x is natural logarithm. That's next time. That's next time.
Okay.
All right. So this function is, as you see, it is a product. It is a product, but you see the u function, the first function in this product, the first factor is actually a composite function because it's 8th power of something. So in principle, when we differentiate, writing it slowly, we should think, okay, x to the 4th minus 3 to the 8th, we differentiate this. So you see, I find it faster than writing dx, dy, dx. Times the square root without derivative, v, u prime v, plus u without derivative, x to the 4th minus 3 to the 8th power, times the square root 1 minus 4x differentiated. So now this is product rule. Now I see I want to differentiate x 4th minus 3 to the 8th power. And I say, okay, now this is composite function. Now I have to use chain rule inside my product rule. So I have to remember that. So the outer function of this composite, so this is composite, the outer function of this composite function is taking to the 8th power. Okay, so 8th power derivative is 8 times the base to the 7th power, as we know. What base? The same base, no changes. No changes here. The changes happen now. Now times, because it's chain rule, I have to multiply by the derivative of this interior function. So I can even write it more slowly, x 4th minus 3 derivative times that square root, of course, plus x 4th minus 3 8th times, okay, square root of something, again a composite function. So square root is the outer function. Derivative is 1 divided by 2 such square roots. That's the reason why I always say 2 such square roots. I never say, let's say the square root of x derivative is 1 divided by 2 square roots of x. I always say 1 divided by 2 such roots. Because when we differentiate a more complicated square root, it's important that this such remains as it is. And of course, times minus 4. The derivative of 1 minus 4x is minus 4. And now to simplify this all, Now, to simplify this all, first of all, we could, of course, take x to the fourth minus 3 to the 7th outside. That might be a common factor. A little bit of algebra again. So the common factor, see, we have a factor this and we have a factor this. Two terms, but the same factor. So I'm taking the common factor, that is x to the 4, okay, I'll use white, easier to see. X to the 4th minus 3 to the 7th power, because that's the smallest one. And then we have 8 remaining from this. Then we have x 4th minus 3 derivative is times 4x cubed, x to the 4th derivative, times the square root. And basically, I am taking this x to the 4th minus 3 to the 7th power out from the second part as well, which leaves me with x to the 4th minus 3, that is the 8th factor. 7 are out, 7 are taken out, but the 8th one remains. These can be simplified a little bit, let's say. So I can say minus 2 and divided by that same square root. And then I can pull these on the same line, on the same denominator. That's something that I can do. If not, we can of course simply multiply, take this, open this derivative and leave it as it is. I personally do prefer to pull things together more nicely on the same denominator using the same line, but at the same time, it's still, if you do without simplifying, as long as you do the derivative correctly, as long as I see the derivative let's say simplified just a little, let's say constants simplified, for instance, then I won't ask you to pull things more like together, because in this unit, what I want to see is, I want to see that you can differentiate. So at the moment, I have to say that, yes, I would simplify this even further. I am not requiring it from you, but I would simplify it. I would simplify it even more. But however, it's at the moment, what matters is that you understand the derivatives and are able to do these. This is a rather complicated one, rather a big one for the beginning. Now, exercises from the lecture transcript. Actually, this is a composite function, as you see, chain rule. Okay, apply the chain rule. So we can say that y derivative is chain rule. Outer function is taking to the 4th power. So this is the outer function, and I start by differentiating the 4th power. The derivative of the 4th power is 4 times the 3rd power, right? I'm differentiating only the 4th power. What is inside is what is inside. 3 minus 2x to the 2nd power, to x squared. And now, because it's chain rule, I multiply by the derivative of this interior function. I multiply by 3 minus 2x squared derivative. And that would be 3 minus 2x squared cubed times minus 4x. Now, this is something that you can simplify. That's minus 16x times 3 minus 2x squared cubed. So this would be, let's say, the nicest way of writing this particular derivative. We take the 4th power, differentiate, and then multiply by the derivative of the inner function. To go back to remind you of some things, so this 4 and 3, this is the outer function derivative. This is the thing df differentiated by du. And the second part is u derivative by x, using the chain rule. So the outer function, the f function, is this. Taking to the fourth power is the f function, and the g function is this. So you take the f function, differentiate, but remember that inside the f function, we do not have x, we have the u variable, the invented variable that describes the expression that is inside. Next one. Again, this is where you should remember some things like, okay, wait. What this actually means, we could write, if you like, 1/2 x plus 2 times x to power minus 1. If it makes things easier for you, the inner expression x/2 plus 2 over x can be rewritten, because this way it will be easier to differentiate the interior expression. So now, y derivative, sixth power is the outer function. If you have anything to a power 6 or anything to the 10th power, anything to whatever power, so you always start by differentiating that power, but you leave the expression in parentheses as it is. So I would say 6 times the same, 1/2 x plus 2 x to power minus 1 to the 5th power, and now times the derivative of the interior function. The derivative of the interior function, as you see, 1/2 x derivative is simply 1/2 to x to power minus 1. Again, you can do it somewhere on the side, by the way. X to the power minus 1. Derivative is minus 1 x to power minus 1 minus 1. That's minus 2. This is minus 1 over x squared. So minus 2 over x squared in there. And yes, you can actually simplify this by going back to some extent. On the other hand, I have seen people who prefer to, first of all, simplify this. Yes, why not? Write this on the common denominator and use, well, then you have to use the quotient rule. Then you would need to use the quotient rule if you simplified the expression in the parentheses. But yes, it's possible. You could think like this. Okay, it's over 2x. Here we have extra factor x. Here we have extra factor 2. So this will be x squared plus 4 to the 6th power. And then differentiate. But then that means chain rule first, and then times the derivative of the quotient. So quotient rule next. If you do it this way, then there's no quotient rule. But yes, it is possible to transform it like this and use chain rule in conjunction, that is together, with the quotient rule. Yes, that's possible. So basically, this is the result. What would happen? That would happen if you did the quotient rule. Of course, you should pull things together. These would be taken together on the same denominator, but basically, yes, of course. That can be done. There's usually, in many cases, there's more than one way to differentiate a function. The more complicated the function is, the more possible it is to have several ways, several methods for differentiating it. Next one, chain rule again. The square root now is the exterior function. I hope that by this moment you already remember enough to say that derivative of square root is 1 divided by 2 such roots. 1 divided by 2 such roots. Times the derivative of the inner function, the interior function. The interior function is this, 2 minus x cubed. Differentiate that, you get minus 3x squared. Minus 3x squared. Remember the 2 derivative is 0, constant derivative is 0. So constant derivative is 0 if the constant stands alone. If the constant is multiplied by a function, then it remains because it has something to hold on to. But if the constant stands alone, then by all means the derivative is 0. So it's difference, there's a difference, 2 minus x cubed derivative or 2 times x cubed derivative. When 2 is alone, its derivative is 0. So we can write the answer, minus 3x squared divided by 2 square roots of 2 minus x cubed. That's perfectly fine. We don't need to eliminate the radical from the denominator for functions. Okay, one more chain rule. All right. So this is, yes, what?
Can you show the last previous page? One more.
Okay.
Okay, thanks.
Now this one. You can think of it as 4 times 1 over v. And the v function is that, x plus 2 square roots of x. So in principle, we can use this special case of, not exactly the chain rule, but special case of quotient rule, in fact. The special case of quotient rule, in fact. Remember that then the derivative would be 4 times minus v derivative divided by v squared. Why not? Why not? So it does not have to be chain rule, or if you want to use the chain rule, you can think of it as 4 times x plus 2 roots of x to the power minus 1. And then you need to differentiate power minus 1. And then the interior function is that. So as a result, you would still get exactly the same situation. So you can differentiate it using chain rule. Here, y derivative is 4 times minus 1 times x plus 2 square roots of x to the power minus 2. That is, at this point, I am differentiating the exponent minus 1 becomes extra factor, and you have the power, you have the exponent, and then you can multiply by the derivative of the inner function, which is 1, x derivative is 1, plus 2 divided by 2 such square roots of x, so 2 will disappear for us, 2 will cancel out. So we can see that this derivative is minus 4 divided by x plus 2 roots of x squared, because the exponent is minus 2. I can write a square in the denominator. And then I have to multiply by this. If I think of this as putting things on the same line, I would have square root of x, and I would have square root x plus 1, for example. So this last part is this simplified. Oh, no. It's this simplified. So you can do it like this using chain rule, or you can use the quotient rule special case. So y derivative would be 4 times minus derivative of v, that would be minus 1 plus 1 divided by root x divided by x plus 2 root x squared. V function squared, v function derivative. As you see, if you transform this part, you will get, again, you'll go back exactly to the same answer. So it's up to you what you use. You may use chain rule for functions 1 over v, or you may use special case for quotient rule, 1 over v derivative. Now, product or quotient rule. This should be simple. So I guess one last time I will rewrite the product rule without differentiation yet, and then differentiate. So we will have 2x plus 1 derivative, x squared plus 3x minus 1, nothing, plus 2x plus 1, nothing, x squared plus 3x minus 1 derivative. And so we have 2 times x squared plus 3x minus 1 plus 2x plus 1 times 2x plus 3, which is the derivative of that last polynomial. And then you can open the parentheses and pull things together. You would have 2x squared plus 4x squared, that's 6x squared. Then you would have 2 plus 6, 8x plus 6x, that is 14x. And then we have minus 2 plus 3, that's plus 1. So yes, it makes sense to simplify polynomials, expressions like this. It makes perfect sense to make them as simple as possible. But however, well, yes, in algebraic situations where you have polynomials, simple opening of parentheses and combining like terms, I would expect you to do it. That's simple enough. This is simple enough. So derivative of first function times second function. So this was u prime v plus u v prime. Or, well, if you like to use those dy dx, I cannot stop you, of course. I still think that this is faster to write down. Of course, there's a little bit of danger if you don't write these dashes, this prime sign, clearly enough. In the next line, you might forget about it. So that's one thing. If you are forgetful, then probably that other notation is more convenient for you. I still say that for fast working, this is the best notation because it helps you keep up a good speed when necessary. Another product rule, let me check the time, 4 minutes remaining. I am not doing this because you understand what is going on here. The file is uploaded, the answers are in it. So you can in fact try to do it yourself and then check the answer. Quotient rule, this would be something very, very nice. The result of this will be something really nice. So let me remind you. Although, well, actually, I would gladly leave it for yourselves to do, but okay. So x squared minus 1 square. In fact, I do have a habit of writing the square in the denominator first. I have a habit because then that's done. I don't have to think about it anymore. The first function derivative is 2x. The v function without derivative, x squared minus 1. Now, first function without derivative is x squared plus 1 times v derivative, which is 2x. So u prime v minus u v prime divided by v squared, of course. So this will be, let us see, 2x cubed minus 2x cubed. X cubes disappear. Then we have minus 2x remaining from this and minus 2x remaining from the other one. X squared minus 1 squared. So minus 4x divided by x squared minus 1 and squared. After simplifying again, something very simple, very nice, and everything works out. Everything works out very nice. What else do we have? This is the same type of thing. This is the same kind of thing. This is something very similar. Again, just the square root that creates a little bit of extra difficulty because you have this 1 divided by 2 such square roots. Now here we have combined rules. Again, we had something similar. I am not doing this now because you see this is the product rule in which in both factors we have chain rule. So first of all, we write it out as a product rule, and then inside the product rule, you see where you have to apply chain rule for the first and chain rule for the second. That's something that needs to be noticed. Here we have quotient, again the same thing, quotient rule with inside the quotient rule, you will have this composite function, so you will need the chain rule for that. Perhaps I'll do this one for you. So the derivative would be 3x squared times the square root without differentiation minus 3x without differentiation times the square root with differentiation and divided by square root, the denominator function, which has to be squared. So that means that in the denominator, we simply have x squared minus 1 without the root after squaring. Here we have 3 times square root x squared minus 1. So 3x differentiation is easy. Now minus 3x. And now we have again the chain rule. Again, the chain rule. So for that square root, of course, the outer function, the exterior function is square root. So we start by differentiating the square root. So it's 1 divided by 2 such square roots. So I keep reminding 1 divided by 2 such square roots, 1 divided by 2 such square roots, hoping that you will somehow memorize it, times, of course, the derivative of the inner function, that is x squared minus 1 derivative is 2x. X squared derivative is 2x. So we see, all right, 2 and 2 will cancel out. And then we have this x divided by square root, which is not so pleasant. So perhaps we should somehow, for example, we can multiply the numerator and the denominator, both of them, by that square root. So in fact, I multiply the denominator by the square root of x squared minus 1 and the numerator, which means I multiply by square root here the first part, and I multiply by square root the second part. So when I multiply the first part, square root multiplied by itself is you lose the square root. So it will be 3 times x squared minus 1 without the root, minus here we have 3x times, and we see we have x from here, one more x, but the square root and this square root will cancel out. So again, see how nice it becomes. You can actually cancel out 3x squared. And so the final answer would be minus 3 divided by x squared minus 1 times square root x squared minus 1. So in most cases, as you see, the rules need to be combined because the functions are very seldom that simple that you can only use the quotient rule, only use the product rule, or only use the chain rule. The functions generally are built in many different ways, and they can be complicated. Even a function that does not look too bad, as in this case, or in F, it starts with chain rule because first of all we see, oh, it's a composite function. It's a cube of something. It's a composite function. So in this case, we would start with a chain rule. No time anymore, but I will just write out the beginning. So we start with the chain rule, and that means from the outside, start by differentiating the cube. That means 3 times the same thing squared, and then times x divided by 1 minus x derivative, chain rule. But now to fulfill the chain rule for the inner function, now you need the quotient rule for that one. So basically, it usually is some kind of combination. All right. So this is where we end for today. Please try to do exercises from your lecture file. I will think about perhaps uploading in a good time, uploading the homework in good time, so that you can start practicing some more, but that will be, let's say, more efficient after Wednesday, because on Wednesday, as I said, I expect you to know very well how to differentiate a power and able to apply these rules, product rule, chain rule, quotient rule, because next time what you will get, well, you actually already have the file in Orthos. Next time you have this list of all derivatives of all elementary functions. In fact, I would strongly advise you for the next lecture, for Wednesday's lecture, print it out already. Today or tomorrow or very early Wednesday morning, have it, because it will be useful for you to have it in front of you to be able to consult those derivatives at any moment. I'm not asking you to know those derivatives by heart. However, the more exercises you do, the more you remember in your brain, in your mind, the more formulas, the more functions, the more derivatives actually stay in your mind. Because when you practice, you consult your formula sheet, you consult the derivatives table, the list of derivatives, but with time, in fact, something settles in your mind. So please do the exercises in the files, because that's actually helpful for you to understand things, figure out things, practice things, and so on. All right then. Please look up and get the list of derivatives for yourselves available. There is the file, and we will use it next time. We will use it next time for practice. So next time, just exercises. I hope to do all the functions, a little bit of all functions, so that you have the general idea. All right then, I'll say goodbye for now. Sorry about the delay, because things went a little bit wrong for a while, but fortunately I was able to fix things. Okay, bye.